Astrocytes, often described as the support cells of the brain, play a far more active and vital role in neural health than once thought. Among their most crucial functions is the regulation of sugar metabolism, specifically their handling of glucose and its storage form, glycogen. These glial cells are the brain's metabolic caretakers, constantly adjusting energy supply to meet the intense and fluctuating demands of neurons. Under both normal and stress conditions, astrocytes act as a critical energy buffer, converting glucose into glycogen and breaking it down when neurons are starved for fuel. But when astrocytic sugar metabolism is disrupted, the consequences can be severe, leading to impaired synaptic signaling, increased neuronal vulnerability, and potentially even contributing to neurodegeneration. In a healthy brain, glucose enters astrocytes through high-affinity transporters and can be used immediately for energy or stored as glycogen for later use. Neurons, while highly dependent on glucose for function, lack significant glycogen reserves. Instead, they rely on astrocytes to help manage energy during periods of high demand or metabolic stress. When energy requirements spike, such as during intense synaptic activity, ischemia, or oxidative stress, astrocytes mobilize glycogen stores and convert them into lactate or glucose derivatives, which are then shuttled to neurons via the astrocyte neuron lactate shuttle. This system ensures continuous support for neuronal ADP production and maintains synaptic function under pressure. The role of astrocytic sugar metabolism becomes especially crucial during pathophysiological events like hypoxia, seizures, or traumatic brain injury, where energy delivery is disrupted. In these settings, neurons rapidly deplete their local energy reserves. If astrocytes are functioning properly, they can compensate by rapidly breaking down glycogen to feed neurons. However, if astrocytic glycogen stores are depleted, poorly regulated, or structurally abnormal, as seen in certain neurodegenerative diseases, the energy gap widens, triggering a cascade of dysfunction. Neurons may lose their ability to maintain ionic gradients, synaptic transmission falters, and eventually, cell death may follow. Moreover, astrocytic dysfunction in glucose handling does not just impair energy flow, it can disrupt synaptic integrity itself. Astrocytes are intimately involved in neurotransmitter cycling, particularly for glutamate, the brain's most abundant excitatory neurotransmitter. The uptake and recycling of glutamate depend on ADP, much of which is derived from astrocytic glucose metabolism. Without sufficient energy, astrocytes cannot effectively clear glutamate from the synaptic cleft, leading to excitotoxicity, a well-known mechanism of neuronal injury in disorders like ALS, Alzheimer's, and stroke. Here again, proper regulation of sugar metabolism is not a luxury, it is a requirement for neuroprotection. There is also evidence that impaired astrocytic sugar metabolism plays a role in aging and cognitive decline. As the brain ages, glucose utilization efficiency declines, even in the absence of overt disease. Astrocytes may begin to accumulate abnormal glycogen structures, or lose the ability to efficiently switch between storage and mobilization modes. This metabolic inflexibility reduces the brain's ability to cope with stress, and over time, the cumulative energetic strain can degrade memory, attention, and executive function. The warning here is subtle but critical. The metabolic health of astrocytes and their ability to manage glucose and glycogen directly shapes neuron survival. If this system falters, whether due to chronic high sugar intake, oxidative stress, inflammation, or systemic insulin resistance, neurons are left without the support they need to survive, let alone thrive. The failure may be quiet at first, manifesting as fatigue, brain fog, or slowed processing, but over time, it can evolve into structural damage and irreversible neurodegeneration. And yet, this also opens a window for hope. Strategies that enhance astrocytic metabolic resilience may prove to be powerful tools in preventing or slowing neurological disease. Interventions such as intermittent fasting, exercise, and diets that improve insulin sensitivity have been shown to support astrocyte function and preserve brain energy homeostasis. Certain bioactive compounds, like resveratrol, ketones, or polyphenol, may also improve astrocytic energy management and reduce oxidative damage. Ultimately, the survival of neurons cannot be viewed in isolation. It depends heavily on the metabolic strength and flexibility of the astrocytes that surround them. Sugar metabolism in these glial cells is more than just background biochemistry. It is the invisible architecture that sustains cognition, memory, and resilience in the face of stress. Protecting and optimizing this system may be one of the most direct ways to protect the brain itself.